Welcome everyone to the Tulsa.net user group. Tonight we have Chris Gardner out of Huntsville, Alabama, talking on demystifying the .NET runtime. Chris, thank you so much for being here this evening. I'm going to let you do an introduction and take it away.
Well, thank you all very much. First thing I want to say before we get started, besides thank you, Sean, for having me out here and getting all the logistics and everything and all the recording and everything done. I'm sure this is going to be great. Anytime I'm speaking, it is fully interactive. So please feel free, whether you're in person there, just shout out to everyone else, or if you're on Zoom, just come off mute, ask questions, ask your concerns any point in time. There's no, at any point, doesn't bother me at all. I'm here to answer you all's questions. So keep that going forward. This is demystifying the .NET runtime, which is, I like to sometimes say this is the most advanced beginner talk you're ever going to go into, because none of the code we're doing is very complex, but looking down at that kind of lower level has a tendency to sometimes be very challenging for people. So definitely, especially because I've been doing this talk now for several years, I am super comfortable looking at MSIL. And so sometimes I forget that this may be almost alien to some people. So just want to get that out first. The obligatory narcissistic slide, I'm Chris Gardner. As Sean was saying earlier, I am the chairman of the DevSpace Technical Conference down in Huntsville, Alabama. We are hoping to be back next year after missing this year and doing 2 years virtual. Looking forward to getting people back in person and back in Huntsville. So look for that coming up soon. There'll be links, all the social links are at the end and all that stuff. I'm also, by day, I am a software products and platform engineering manager for Accenture. Yes, that is a job title that only a multinational company could love. I specifically work in the PPES division, which is the product and platform engineering services. And basically, we're like a small consultant shop built into a mega corporation. So I'm fundamentally just a consultant. But given all that, because all that's fine, and we can talk about all that type of stuff later, but let's get to what we're here for. And we're going to start with a very brief history of time. We started with punch cards, and that was horrible, which is why the girl on the left is not very happy. And so then we got to assembly language, and that's why the girl on the right is a little more happy. For those of you who don't recognize the picture, because it has come up that I am from Huntsville several times, this is Margaret Hamilton. This is the source code for the Apollo rockets, which she was the lead engineer and manager of, wrote large quantities of it. So there's my little bit of Huntsville thrown into the conversation. Anyways, so then we took that assembly language and we turned it into high-level languages. So things got even easier. So we had this big monolith. And this is, you could just write this and get the other one. This is 100% compilable C code. And if you compiled that C code onto an x86 processor, so 32-bit, not 64-bit, this is the assembly language you would get. I like to use this example just because I like to point out my favorite line of code ever, which is x equals x plus 1. If you're not familiar with that line of code, we like to call it the fundamental lie of computer science, because there is no way x will ever equal x plus 1. And if you are comfortable with this line of code, then you will be okay being a programmer. This is when I would normally stop for a quick chuckle of everybody, but it happens. So the way this whole coding thing used to work, I've been doing this professionally like 25 years now. And when we first started, what would happen is that you would take coffee, you would give it to a programmer, and the programmer would produce code, right? That is the programming pipeline. We have to do this because we have to have our coffee. If you were in here during the introductions, yes, I was even drinking a cup of decaf, because I drink decaf because I like coffee that much. Only after 4 p.m. I'm not crazy. Yeah, no, Diet Coke. No. Believe it or not, I gave up sodas years and years ago. So I just have to find other bad habits to take up its place. Anywho, more appropriately, after we do that, we then take that code and we hand it to a compiler, and the compiler turns it into a program, right? And we do this because computers can't compile coffee. We've tried, we've been working on it for years. However, it is not possible to get the computer to compile the coffee. I'm sure the first person to figure out it's going to get a Nobel Prize. If you ever wanted a Nobel Prize, figure out how to get a computer to compile the coffee. Can't be that hard, right? Right. Anyways, the big point behind all of this is that back in the day, old languages like C and C++ produced programs that depended on a specific architecture, right? Because it was using that assembly language, which is very specific to the actual hardware. So to run on new hardware, you actually had to take the code and move it to the new hardware and recompile it for there. Theoretically, you could actually tell the compiler, hey, I don't want you to compile it for this architecture, compile it for this one, and do it all in one box. But in practice, that actually wasn't done very much. By contrast, most modern languages run inside of a virtual machine. So you end up with this VM that acts as a hardware abstraction layer. So the code is compiled into assembly language for that virtual machine, and then the VM translates the assembly language into machine language on the fly. This was, to the best of my knowledge, the first language to ever do this, which was its claim to fame, was Java with the JVM and bytecode and all of that, where they said, "Hey, we're gonna take the first part and go." So with all this, C# runs within the .NET or .NET Core, or now just .NET framework. So the C# compiles down to an intermediate language called MSIL, and the .NET framework runs the MSIL. Yes, there's a slight hand-wavy truth there, but we'll get to that in a moment before people start yelling at me. I know there's a factual inconsistency in this slide. It's there on purpose. So when that happened with this timeline, we had, version 1 came out in 2002, and then we had C# version 1.1 and 1.2, which was, I believe, I'm trying to remember what were in all these versions. But that came out in 2003. In 2005, we got 2.0, which I believe is where generics came in. 3.0 didn't have much of a huge improvement, but there was a 3.5, which was just called 3.0 Link, that came out a year after that, which is where we got Link. 4.0 is async and await. And I'm not even going to try to remember what was in .NET language 5 and 6 and 7 and all that. But notice that these are going up. But the funny thing to notice is that when we go up with all of these, you get the .NET framework version, and they're coming up mostly in cadence, but they're doing a few things slightly different. So they stick part for part. Then the 3.0 Link is where you get our first breakdown because of the 3.5 version of the .NET framework. And then we get 4, and then 4.5, 6, 7, and all of this, 7.8 now. And of course, now it is worth mentioning, if we were talking about .NET Core, it had its own framework, it had its own version of what was going on. It's not called the framework at that point in time. We'll get to all that in a second. And then the new .NET 5, .NET 6 has its similar version of that. But all of that will be wrapped up in a second. And the reason I have to put it that way is because now I have to say the lie from earlier. So the .NET framework doesn't actually run the program. The .NET framework is technically like the VM. And similarly, if you remember Mono, or what is now Xamarin, that is its own VM, which is just that hardware abstraction layer. And what's actually running the program is what's known as the Common Language Runtime. And it's called the Common Language Runtime because even though we don't see it as much these days, because the only .NET languages that are really prevalent are VB.NET, C# and F#. When .NET shipped way back in the day, there were something like 28 .NET languages. There was a Java.NET, there was a COBOL.NET, which, believe it or not, Fujitsu still maintains. But there were a bunch of other .NET languages that would do the same thing. They would take standard code for that language and compile it down into MSIL. And it was the MSIL is that common language, and it's the Common Language Runtime that runs the program. So with that, we have to add in a new column, which is the CLR version. And what gets weird with that is that you notice, version 1 had version 1, 1.1 had 1.1, 2 had 2, but then we get to strange things where for 3 and 3.5, we just still had version 2. What was going on with that? And then we hit version 4, and ever since version 4, we've been on the Common Language Runtime version 4. The way that this has happened is that there came a point in time when the design team realized that if they're updating the CLR version and that VM, then to have compatibility with old versions, you had to keep upgrading the VM, which is why back in the day you had to install framework version 1, framework version 2, and then framework version 4 if you wanted programs written in all those compatible. But around the time of version 4, they really realized a lot of these new features we're adding to the language we can actually do with compiler tricks. So when you compile the code, instead of there being a optimized way, we'll get to that in a moment, optimized way to do that one particular function, we can just write the code that's kind of syntactic sugar that does it for you, so that the language of C# becomes more terse, but it ends up technically making the program maybe slightly more verbose because it expands out to more lines of code, which is a lot of what we're going to get to in the later part of this talk. So with all that, what does this all mean? Well, we have to know what's really going on behind the scenes if we want to understand what's going on, what sort of compiler tricks are going on, et cetera, et cetera. So knowing is half the battle. And I particularly like this one because it's not the tried and true, use the force, Harry one. So let's get right into it all. Everybody on board. This is when somebody comes off mute and say, yay, code. Oh, you're killing me, Smalls. All right.
You got to give me a minute. I was chowing down on some barbecue. Oh, sorry. Yay, code.
There we go. All right, we're at it.
All right.
So this is the way this is going to work. I'm going to pull up some little programs I wrote. No, these programs are not available on GitHub. And the reason being is because they're trivial code. And the idea is I want you all to go play around with these things. And it's not the code itself that's the interesting part. It is looking at the MSIL afterwards. So you're like, but Chris, how do you look at MSIL? And I'm going to say that's a great question. Because what is going on is there are two primary ways to do it. And I use both depending on what I'm doing. One of which is a product from Telerik called Just Decompile, not a sponsor, but it's a sponsor. I am a Progress Ninja, full disclosure, but this has a much nicer user interface. You can get into, or like you can drag down into the documentation on the individual methods. The visualizations are a little cleaner, et cetera, which is why I like to use it for this talk. Having said that, it does have a few limitations. If we look at our languages here, after it decompiles, it only does Visual Basic, C# and IL. And I also do a lot of stuff in F#. So there is also a program you can get, and I probably have it in here somewhere if I just right-click one of these. Let's see if I've installed it on this computer yet. No, I have not. There's a program oh, wait, maybe it's because I hit the wrong one. Nope, okay, I haven't done it yet. There's a program you can get out of the App Store. Literally just go to the Microsoft Store. It's called IL Spy. It will actually hook into Visual Studio, and then you can get the same type of support by just selecting a library, and there'll be a little open an IL Spy icon here. And it will open up that way. IL Spy is not quite as user-friendly, being a free open source type thing, but it does have F# support. So that's kind of why I'll go back and forth between the two. So either of them will work fine for any of this stuff. So everybody on board with what we're doing. Now, how many of you saw when I had this open a second ago and were like, ah? Go ahead, you can admit it. It's fine. Okay, good. We haven't scared everybody off yet. So I am not expecting anyone in here to be able to natively read intermediate language. I'm going to guide you through all of it in baby steps. The idea by the time you're done is, one, I want you to be able to see certain things that are going on between the compiler and the runtime, thus demystifying the .NET runtime. And then also, just if you're at the point where you're like, why is this weird thing going on, start to give you a comfort level with all this stuff. So we're going to start with one of my favorite examples ever because it's so small and trivial, and it's going to use a couple of my favorite little pieces here. So we've just got a little bitty console application. All it does is hello world, right? Because I don't care about the actual main application for a moment. But what I've done is I've created 3 methods inside of it. One of which is called unchecked, which forces an unchecked block inside that returns x plus 1. I've got another one called checked that creates a checked block that does the exact same thing. Now, before we go on this part, I'm not going to say, does everybody know what checked and unchecked does? Because then nobody's going to admit it if they don't know it. So I'm just going to tell everybody, y'all are off the hook. But what this does is this tells the runtime, you'll admit you don't know? Okay, good. This tells the runtime whether to explicitly perform the overflow check or not. So if you are forcing yourself in the checked context, if you do this operation and you overflow, so if x was equal to max int, or int.max value, and it overflowed, it would throw the overflow exception. In the unchecked context, this tells it to explicitly not check for the overflow. So if we did x equals x, or if we did, max value plus 1, it would overflow, so it would return min value because of the overflow happening. So that's just a minor thing, and it's generally considered sometimes good practice to do checked contexts in debug, so you're always catching it, but then because exceptions can be expensive, just go to an unchecked at release time to prevent crashes. And we can look at what's going to happen with those. We'll come back to this little unknown guy here in a second. But we can look at what's going on with that by just looking inside of our MSIL. I don't know why I have 2 open. I'm going to close one. Okay, now I only have 1 open. All right. So this is what a program looks like in MSIL. And you will notice down below, it was supposed to be. I guess I did it in the other one. So we have our unknown hiding. But for example, here's our main. Inside of our main, we got places where we could pass in the arguments. That's just our argc that everybody's used to on a command line app. Says it's the entry point for the program. Loads the string hello world into a register. Call system.writeLine. Putting that in there. Returns. Right? That's our main program. That's what it looks like in MSIL. Theoretically speaking, this load string loads the pointer onto the stack, and system.console pulls the value off the stack. We'll get more into that stuff later. Don't worry about that level of detail right now. What we care about right now are those 2 functions we talked about. So this is in release mode. This was debugged in or compiled in release mode. The reason I can tell is because I'm willing to bet this one right here is the non-release mode version. Yep, we'll get to that in a second. So coming back into here, what it's doing is when we enter the function, we're passing in a value called x. We're loading that argument. So we're loading that 0th, so first argument, out into the stack. We're saying load an integer 4 that's a constant with the value of 1. So that's my plus 1. So we put our input parameter in. We put in our 1. We say add those 2, and if necessary, overflow. So we've got add.overflow. And then that's going to end up leaving the value on the stack, and we say return what's on the stack. That's our method. So what's worth mentioning is that now if we do the exact same code in unchecked, you'll notice that the command is just add. It's not add overflow. So this is a place where, depending on our code, the code is actually physically changing the instruction we're doing. We'll go back to the debug version in a moment. I normally have the debug version open first, because that's another very interesting thing to see what's going on within these things, within a simple program. But now the question is, if we come back to our unknown, if you didn't see that, nobody saw that code. If we come back into our unknown, what is it going to do? Because if you remember in our code, it doesn't specify. It just says, as a lambda, return the value x plus 1. So is the value going to be checked or unchecked? Both adds are still 1 byte. Yes, that is a good point, James. That is not necessarily the point I'm getting at with that. This is not an efficiency area for size or efficiency on the computer. This is just talking about kind of how the stuff's being written. But that is a very good point. But does anybody have a guess? Normally, if I was doing this in a room, I'd be like, show of hands, but that's kind of hard right now. But just think to yourself, take your word for it. When we look at it, is this going to say check for the overflow or not, if we didn't specify? And we will go look at it. And by default, it does not check for the overflow. Now, I said two things that were a hint that are also a lie, and then we'll get to what the real answer is. One is, I said I compiled this in release mode, because that used to matter. In way old versions of the runtime, if you send in the debug parameter during compilation, it would use the overflow version. And when you did it in release, it would not. That's where I made that comment about earlier. That behavior has actually changed in more newer versions of everything. For reference, since I don't think I mentioned it, this code is compiling with .NET Core 3, just for disclosure. But what's going on here is, if on this one we look in our properties for the project, down here in some of our advanced properties, there is a checkbox right here that says check for arithmetic overflow. So whether or not it's choosing the check for overflow or not is based on this checkbox. So if I check it, it'll check it for arithmetic overflow. If I don't check it, it will not. There are other places in .NET that I'm not going to bother to look up because it's not important right now, where based on compile time settings, you can change the behavior of what the actual MSIL produced is. A lot of it comes into, see, because we're in release right now, so it's saying optimized code and all that. But when you start doing these conditional compilation symbols, this is where you can actually add flags to the compiler to change that default behavior. And in reality, all this checkbox does, because it's a common enough one, is it adds a flag right here. You believe adds are unchecked by default? Again, it's a 6 of one, half dozen the other, because it's, if you just open a brand new project, I believe in debug it is set up to be like let's just do it real quick. File, new, project. Just give me a command line. Console application, don't care which one. Yes, you can call it 2. That's fine. Well, let's have fun. I don't have 6 on here yet. I don't have 6 on here yet. We'll still do 5. It'll be closer to 6. All right. Properties, there was nothing up my sleeve. Build, advanced. So right now we're in debug and it is not checking. Change the platform to release. And it's still not checking. So right now the default is to not check for overflow. There you go. Close that out. So that's where we're getting with that. Another thing I want to point out with the easy example, just about everything else in this that we're looking at is built in debug mode. And so one of the things I want to point out that we're going to have to look at as we go through it, it's if we come here, this is the exact same code just compiled in release mode or in debug mode. And what you'll see all over the place are things like this. So remember our checked method before was just this line, this line, this line, and this line. So what's going on is, first of all, we have these no-ops. Does anybody have any guess what no-op is and why they're there? Again, you feel free to come off mute to talk because typey sometimes takes too long.
It's no operation. And
It is no operation. Why is it there?
You used to use it for timing back in the old days.
It is not used for timing. That is a good guess, though.
I would say alignment, although I'm not quite sure why it would need to be there.
It is not there for alignment. Now, your clue was they're here in debug mode, but not release mode.
Is it places for the debugger to hold on?
It is places for the debuggers to start hooking into places. Yes, that is 100% what it is. So all these no-ops littered all over the place are giving places for the debugger to inject in code to say, hey, when you get here, either perform a halt and stop, throw a, interrupt request, or whatever it is that it's magic doing. I have not tried to actually look at MSIL that the debugger is messing with. Sorry. But this is so that the debugger can get hooks in places. And as we get into more complex code later on, like here's an example right here where there is one mid-function. Here's an example right here where there is one mid-function. Generally speaking, there's at least one no-op between what would have been every discrete line of code, so that it gives the debugger a place to attach it. So I figured that would be something kind of interesting. But on top of that, when we get to our Lambda, notice there are no ops in there. Because remember, unknown was done as a, well, technically not a Lambda, what expression body statement. Because it's just that kind of one line in and out, there actually doesn't give it a place for those to go in. So if you're wondering why when you're doing weird things with link and you want to debug like the method inside of link and you can't, it's because the way it handles anonymous functions and things like that doesn't leave room for the hooks to come in, and you actually do have to do weird things to force them in there. So there is your help for why sometimes your debugging gets weird. Have you already learned something and made it worth the fact that we're not eating Sean's barbecue? Very good. All right, let's get to some more examples. Are there any questions about anything we've gone over so far? Because it's just going to get slightly more complicated as we go along, and more deep. So I want to make sure that there are no more questions. Somebody, all right, there was the yes that came up. So let's see if we can get the question typed in, or feel free to come off mute and just ask it. All right. Feel free to pipe in. I'm keeping my eye on chat down here, and I'll see if it comes up. So let's get to our second example. No questions from the room. So let's go into this one, which is talking about strings. Some of these I'll run and some of them I won't. You'll see why when we get there. So here I took a bunch of strings, and there's 2 points behind this example. One is, what is the really weird, strange thing about strings in .NET. They have a very unique property that only strings have by default.
Is it
Technically, it's two
immutable?
properties that bounce off each other.
Let's say they're immutable.
They're immutable. That is one of the two properties. That is one of the two things I was looking for.
Yeah.
What is the other thing?
I always say it's a reference type pretending to be a value type, but I'm not quite sure that's.
That is 100% the other thing. It is the only, keyworded value, literal, my brain just died on the word, but you know what I mean, type that is actually a reference type and not it is not sealed. I don't believe it's sealed. Is it sealed? It is sealed, but the seal doesn't matter because I think the ints and all that are sealed too. And if you don't know what I just did, I hit F12. But yeah, it's a reference type, but it's because of its immutable, it's treated like a value type like everything else. So it does some weird things, which is why we actually look at strings a lot. So here's what I'm doing here. We're doing a lot of heavy lifting with this example. Gonna be fair about it right away. So the first thing I'm doing is I'm creating a constant string called const string, so we can find it. The value is const string. I'm then creating a static read-only string called static read-only string with the value static read-only string. So you can see what the difference between those two are. Sealed for freshness. Yeah, let's stick with that. All right, we now are creating one that is a literal string that we're actually going to put in the value called literal string. And then we're going to create a couple other strings where we're copying each of them over to kind of show how it's handling the memory and various parts of it. Makes sense to everybody? Anybody got any questions about the way we set anything here up? All right, good. So let us go back into here. Close these down real quick. Just use strings.dll, strings namespace program. All right. So the first thing we need to add, which is going to be weird, is here we are saying we have this field that's a private static literal. Literal is what it's using for const behind the scenes. String called const string, and there's our hard-coded value, right? It makes a reference to it right away. But then for our field private static, we have init only, which was our read-only string, static read-only string. Have any of you noticed in the newer versions of .NET, they added the fact that you could make a property and a init, I believe it's an init property, or there was an init modifier. I don't remember the exact word off the top of my head, but they stole it from in the MSIL. You could specify read-only things were init only. So they stole init since they had already used read-only to say you can only do this at the beginning. Yeah, I knew it's in one of the newer versions of C#. Gary's saying C#8, so don't quote me on that, but that's where that terminology came from. It's from in here where we're saying you can only initialize this. Now, originally, because everything's an object, so our main static thing is an object, there's this, constructor, which literally just says call base object constructor. But this new constructor showed up called CCTOR. This is our static constructor. So even though we didn't specifically declare a static constructor, because we are using a static variable, this actually gets put into the static constructor when it builds it, which is what this is. So here's where we're saying, load this string and set the string field's name to this. This is where we're setting up that static read-only. So far, so good. Here comes the fun part. We've got our args, which we're not using. Then notice here at the beginning, it's saying, I'm going to localize some I'm going to initialize some local variables we're going to give them names. So we've got string 1, string 2, string 3, string 4. This is literally, that's 0, that's 1, that's 2, that's 3. That's it internally using symbolic names. So, of course, no operation. Here, notice as we're setting the first one, so load the string, literal string. Notice it actually has the literal string there because it was a string literal, right? It wasn't initialized in memory anywhere. And store it into 0, which is our first variable. So it's storing it into here. Okay, so we're copying that value over. Now's when things get fun. Load const string and load it into 1. So here, even though up here we declared that it was a const by name, this is mostly for decompilation purposes. And it gives it a memory location, but it inlines the value, which can have its own set of problems or whatnot. There's another really strange property of strings that we'll get into in a moment, but don't worry about that right now. Anywho, here we're actually seeing the reference to our static read only. So it's saying load the static field that we've declared and set its location. And then the one I really like at the bottom is here we're using literal string. So it's saying, hey, load whatever you put into that first variable and store it in the third variable. However, we mentioned previously that these are all references. So these are just pointers. So somewhere on the heap, it declared literal string as a string and threw it in the heap, same way it does a const. And there's a pointer to it. And these are both sharing that same pointer. And the reason it can do that is because strings are immutable. So to save room, it declares one copy and just always shares a pointer to it. And if you change that string, which you can't do, but if you change it, then it just creates a new one in the heap and gives you a new pointer. Everybody, does that make sense to everybody? Everybody good with that? So here's where we're seeing really how consts are being dealt with, how statics are being dealt with. It shows that static constructor that comes up, shows how local variables are handled, plays around with that stack and everything more. Know a lot of went on there. So any questions before we move forward? This is when we pull the editor. You can just, trim down the parts in the middle where nobody's asking questions. So yeah. No, I've never done that to my YouTube editor. Anyways, because I'm my own YouTube editor. That's why I've never done it to the YouTube editor. All right, let's go to the next example. Where the visuals right there. All right, here's fun. Reflection is one of my favorite things. I use reflection way too much. So reflection is your ability to bypass compile time and go to runtime. So you can do a lot of things you're not supposed to do there. And here is one of my favorite examples of how there are things you cannot do there. So in here, we're going to create this just little static class. We'll see why here in a moment. Inside the static class, we have this internal static read-only enumerable. And when we first talk to the static class, it's going to set the value of that enumerable to the list 1, 2, 3. Everybody good so far? Nothing strange going on there? Now, using reflection, we are going to, inside of our main program, so we're in a different class. We're going to get the type of that class. We're going to go find this field, this internal field, called ints. And when we're going to set the value of it, which is internal, static, and read only. And if you really want to have fun, I can actually make this thing private, and this still works. We're going to set the value on the static version of that class, which is what the null means. It means the static version, to the value 1, 2, 3, 4, and then we're going to print out the numbers. So far, so good? So first of all, just be thinking about it while you get everything set up. Will this print out 1, 2, 3, 1, 2, 3, 4, or will it crash with some sort of exception? Doesn't matter what the exception is. So, but be thinking which, feel free to put in the chat which one you think it is, but just internally, think about which one it's going to be. We are going to make this the startup project real quick. Yeah, there we go. Set a startup project. And 5, 4, 3, 2, 1, we're going to run it. Oh, it went to build it. And let's see if I will just, yeah. And we got 1, 2, 3, 4. So we actually got in there and started changing things, which should set off your spidey sense. There's a lot of things that went on there that really shouldn't have happened, right? So what is going on here? Is this going to complain? Oh, it's not going to complain. You know why it's not going to complain? All of these are the debug versions that are open, and I think, yeah, I built the release version. Ha ha! That's why it didn't complain. All right, so we still have our static class, which we'd mentioned already, right? And here's where it has that inits assembly static field only. It's within the assembly. Like I said, assembly is this way of doing internal. It's saying it can only be seen inside the assembly. If I'd have made it private, same stuff would have happened. And then here is just my initialization of that. Yes, it's long, complicated, local MSIL calls. Again, we're not going to worry about that too much. Because it does some weird optimization things. That's why I don't want to go into it too much. But inside of our program, whole lots of weird things happen. So what is actually going on with this thing? Through the reflection, we say load the token from reflection static class. So we're loading that, getting the system type of int. So here is where we're actually doing that's that first line. Here's the get field, right? So load the string ints. This constant 40 is the values of these two enumerations added together. That's the flags value of public, which is 32, and static, which is 8. That's where the 40 comes from. And then we call get field. So this is loading the parameters for that, doing get field. We got this value of 4 in here, new array, duplicate it, load the field. This is creating this. And then it comes in here. So what's going on here behind the scenes, which is, and then the loop is where the loop is where I'm printing it, right? What this is doing, which is very subtle, which is why reflection is really dangerous. You can do a lot of things you don't want to. I even have a very infamous function I have inside of a test DLL that I pull in sometimes that is an extension method on object called get private field and get private property and set private field and set private property, that this code is so boilerplate that you can do this. But what that init is doing is it is saying we're initializing a pointer into the heap for an enumerable, and it, does its initialization. And so what is read only as far as this is concerned is the value of the pointer. You cannot change the value of that pointer. However, using reflection, I can go in here and change the memory the pointer's pointing at. So that is what you're actually doing in here, is you're going in here and we're saying, I'm going to create, that's where this is, this new array, which is what the enumerable is using. And then I'm going to go into memory and change the value in the memory without changing the pointer. We're just changing the value that the pointer is pointing to. which is why you can get yourself into a lot of trouble with reflection. I used to have an entire talk called the Great C# Quiz Show, where I went very systematically into how this stuff was going at a more high level. And we did like, can you change it here? Can you change it here? I'm thinking here soon, I'm going to turn that into some YouTube stuff. So maybe keep an eye out for that, because my YouTube's impossible to find because I don't have very many followers. Follow me on Twitter. I'll post when they exist. But what you're doing is you're changing the values in the memory. You're not changing the pointer itself. And that's what this is going on to. Any questions about that? Because the next thing we're going to do directly comes on top of this one. Heard somebody come off mute. All right. So speaking of that, here's one I like to call pseudo-const. So what we're going to do this time is inside of our program, we got a public static read-only int called try me. Right? Gave it the value 119. That will make sense in a moment. We're going to write out that value. We're going to do the same thing. We're going to go in the program. We're going to find try me. Right? I didn't even hide it as well this time. And then we're going to set the value of this static field, the static read-only field, to 911. Right? Because this would be an emergency. And we're going to write the value. And then I think I originally had a version of this that was in .NET Framework. The read key was there so that the program wouldn't go away. So when I run this, again, think about it. You don't have to actually say in chat if you want to, come off of mute if you want to. But when I run this, is this going to print on the second one for here? Are we going to print 119, 911, or will we crash before that? Which one's going to happen? While I do that whole reset the startup project, is it actually built? Everything seems happy. So we got somebody, at least somebody saying it's going to do 911. Let's run it. And boom, field access exception. Yes, it crashes. So, and the fun part is notice it crashed here, although it's lying. It really crashed here. Cannot set init only static field. Try me after type pseudo-const type program. So it's saying it can't do it. So why could it do the other one and not this one? Go ahead and let this close out. Did it? Unchecked, check deal. Oh, just who cares? And then it went away because I didn't reload it. Because programs. All right, so inside here. Oh, wait, I have to actually go inside the program. Again, static constructor, loading string. Here's our static read only, etc., etc. The weird thing to look at here, and let's see if I can find exactly where it is. Here's where it's loading that value into the field there. STS. Notice the tooltip here, which I will read out because there's no way I can make that one bigger. Sorry. But it says replaces the value of a static, come back here, static field with the value from the evaluation stack. Because this is a value type, its value is held on the stack raw. When we're dealing with the reference type, the value that's held on the stack, because it's all on the stack, is the pointer to the heap, which is why with reflection, I was able to go to the heap and change the memory. But since this is just the value on the stack, and I'm not allowed to change the read-only value on the stack, that's why it crashed. And that's why I like to call it as the pseudo-const. Because notice in here, it doesn't actually list it as a constant. But for all intents and purposes, when you have a value type that you set as a static read only and not a const, it will fundamentally act as a const because it is storing the value, not a pointer to the value. It's a subtle distinction, but it's a very important one. So, I mean, and that should give you a good idea of the way kind of that memory gets handled back and forth. Anything that's a value type, this is a lie, but we'll correct it in a second. Anything that's a value type is stored on the stack. And when you say it's read-only on the stack, you can't change it because its value is there. Anything that is a reference type is stored in the heap, but the stack gets a reference to that pointer to memory in the heap. So you can go to the heap and change the heap as long as you're not changing the pointer on the stack. Now, the reason I said that's a slight lie is because while any sort of value type is on the stack, if you make a struct that is a value type, its value is on the stack. But if the stack contains, or the struct contains reference types inside of it, that reference type is still just a pointer to the heap. Which means you can play around with it in memory and do bad things with reflection. Are we still good? Any questions? All right, I think we're going to do 2 more of these, just looking at the time, because we're already getting kind of close to over. You wrote a blog post where you argue we should stop saying stack and heap and instead use over here and over there. It's the same thing, yeah. The reason they're called the stack and the heap is just it literally refers to how the memory is organized. So if you've got one of those like masters in computer science like I do, and you understand exactly what all those data types are, it actually accurately describes what they are and how they're being used. But for your standard programmer these days, where that type of data nuances has been extracted out and nobody cares about it anymore, and I'm saying this pretty much as a good thing. You know, we've evolved computers to where that's just a specialized area for a certain subset of people who write programmers, or I mean write compilers. That's why they're still called that. I do see your point on that. Let's talk about chaining real quick, because this is a fun one. This is me complaining about the .NET spec. This one we don't have, well, we can run this one. We might run it. We'll see. All right, so I got this little thing. It sets up 2 values, x, which is equal to 12, y, which is equal to 10. I'm doing them in binary. You will see why in a minute. We're going to display the values of x and y, which is up here. All it does is it write lines x equals x, y equals y. We are going to have a broken function, which is going to perform this thing right here. Has anybody ever seen that before? And while somebody's ick, it's not as ick as you think. It is one of the most beautiful, elegant lines of code I've ever seen in my entire life. And C# completely demolishes it. This works perfectly in C and C++. We'll get to that. But then we're going to display that value. But then similarly, we're going to break it down in our working version into 3 separate lines. So we're going to do that, then that, then that. And technically, yes, that is the order we're talking about here. It's technically doing that. So it's going to XOR X and Y and put the value in X. Then it's going to XOR Y and X, which now has a new value, and put it in Y. And then it's going to XOR X and Y, which has their 2 new values, and put that value in X. Anybody have a guess what this method does? Since I didn't put anything in here that gives up what it does. Exchanges them. Yes, that is 100% what it does. For any integral type, it is a lightning fast piece of code that can swap the values of 2 variables without having to use an intermediate value. And since it's doing an extremely low level, very fast optimized memory, or not memory, but processor command, which is XOR. XOR is one of the things the processor can do very fast. It is lightning fast. There's no allocating memory, copying a value over, doing all those copies. It's just literally 3 math operations, which happens that fast. However, this does not work. And the reason being is because if you go deep into the spec of C#, you'll notice something odd. Since I'll run it. We'll run it so you can see the values. So the one that works, X ends up being zeroed, but the Y does get moved over, and then it works in the broken apart one, right? Let's get those a little bigger. It's the original. There's them swapped by separating them. Y gets demolished in the process, or X gets demolished in the process if you do it using the chaining technique. All right, so what's going on here? This is a subtle one. Would it work with parentheses? No. We'll get to that. That is a good question, though. You're thinking correctly. I like where your mind's going with this. Just to be fair. All right, inside the program. Here is the broken version. Now, this is going to be extremely subtle. And so we're going to have to talk about the stack a lot. Sorry. Have any of you ever played around with a calculator or something that does reverse Polish notations where you give it the 2 parameters, then give it the operation?
Yeah.
We're about to be doing that a lot. Just to warn you where this is going. So we pass in X and Y. X is argument 0. Y is argument 1. As we come in here on the completely inlined one, we load X, we load Y, we load X, we load Y. We do an XOR, we duplicate the value, we store the value in X. We do the next XOR, we duplicate it, we store the value in Y, we do the next XOR, we store the value in X, and then these 2 loads are just to pass the values back out. That's loading them so that we can call to display them. Does anybody see the subtle bug that's going on there? It's not a bug. It's actually written into the C# spec. I shouldn't say bug. All right, let's look at the one that works. We load X, we load Y, we do the XOR, we store it in X. We load Y, we load X, we do the XOR, we store it in Y. We load X, we load Y, we do the XOR, we store it in X. X and Y, yeah, Gary said X and Y are loaded twice in the first method. Yes, but it's the reasoning why, and that's what we're getting into. But you did notice the subtle difference between the 2, and that is the important part. What we're doing here is, by default, C# says that if you have a complex statement, especially statements that have like multiple sets and things like that into them, the values of all the operations for the entire line are set at the beginning, are fixed at the beginning. That's why here, when we say we're going to do X, Y, X, Y, that's why it's fixing the values of X and Y to what they were at the beginning of the statement. So when we do the XOR, which means it pulls these 2 off, performs the operation, when it duplicates it, that's it saying, I'm pulling that value off the stack, but leaving the same one on there. This is a trick of the operator assignment operator. It's saying, perform the operation, but give me a copy of it that I'm going to do something with, but then leave the value on the stack. But yeah, what this one's doing is that's loading the values of X and Y all up front. It's not getting refreshed with the operations. That's why it doesn't work. Now, most of you would say correctly, why would you do a crazy thing like this? Which is a fair statement. Not going to argue that one. One is because you can get some insanely optimized things like this if it works correctly, although that's not too bad. But also, the assignment operator is an operator. An operator returns a value, always. So the assignment operator returns the value it assigns. And there are certain places where that knowledge becomes very handy. My personal favorite is when you're assigning a value out of something into in the conditional part of a switch statement. So like switch int x equals 3 or x equals something else, and then that something else is what's switched on, and then you have the copy within the switches, which is pretty close to what the pattern matching syntax actually does under the covers. So there are valid uses for it in knowing this, but you have to know that if you're chaining operators, another example of that you may have seen, I'll type it in. I'll just tell it not to say it. If you do like a int, you can do, let's just say int x, y, z, and then say x equals y. If I can type today, you know, that's complete. Oh, okay, that's not completely valid just because I had already used x and y. Yeah, I can't type it. Yeah, this is perfectly valid, right? So we're saying declare 3 variables, set z equaled it, but then cascade that value down, right? There are other weird cases where stuff like that happens. Anywho, get rid of all that. Last one we're going to do, because we're running way over on time. And this is just a simple one. We don't have to compile. We don't have to run anything. We're going to do a simple lock, right? We have a program here. We're declaring an object, which is our padlock. It's just our standard locking object. And then we're going to come in here and we're going to say lock on the lock item and do our hello world. Why would you want to do this? One, because this is the perfect example of syntactic sugar. This is also the same type of thing async and await is doing. But if you run the same experiment, and I encourage you all to try it at home, if you run the same experiment with async and await, the syntactic sugar it produces is incomprehensible. So what does a lock actually do? So all we had was 2 lines of code, right? We did a lock. We did. There's our object, which is our lock. It's being declared inside the static constructor. We have got our normal constructor, and then we come in here. And for those 2 lines of code, we're going to ignore that. We ended up with all of this. Because this is the syntactic sugar that the lock command performs at compile time. We're loading the padlock, which is our locking object. It threw in a try block that then enters a monitor, which is kind of like a semaphore or mutex. It's one of those special things that ensures only one piece of code can get in there at the time. We have our normal hello world. We then leave our monitor. And then here is a finally that says, hey, just in case, here's our exit. So all of that gets injected in just with that lock. It just adds that code around it. The reason why I said the async await one, even though people find it more interesting, is more incomprehensible. It does this same type of thing, except for it creates a loop that sleeps, wakes up, queries the status of the thread, that's running, compares it against values in a switch statement, progresses along. The amount of stuff it sets up is huge. And doesn't fit nicely on one screen like that. But when I was talking earlier about compiler tricks, because this compiler trick has been there and in the language since version 1, this type of lock. Side point, those types of locks aren't safe for certain types of things. Look up online. I don't have time to go into it now. But you really shouldn't be using locks like that. Use like a read-write semaphore light or something like that. Anywho, doesn't it? Yeah. Create a whole class just for the function, pretty much. But here's where, like I said that. So like anytime you're doing any of these syntactic sugar type things, like some variable question mark dot, it actually writes out in the code the null check to return null and then otherwise keep going. It's just injecting that code in. That's why I made the point that since these things aren't being built into the language, so to speak, and they're compiler tricks, sometimes these things, and I'm not saying it's a bad thing because they're writing the code more optimized than you ever will, but that's why some of the same code ends up being much larger when you compile it because of all of this stuff being injected in at compile time. And sometimes just looking and going, hey, maybe if I did this one thing myself, I could manage it a little better in some things. Anyways, we've been going now on this stuff for at least an hour. And the last one I have canned, which is this volatile one, is such an obscure keyword. There was a point in time you had to know what it was. It prevents optimization. Anywho, where's PowerPoint? Let's just get back to this. That's all I've got. If y'all got any questions, please ask questions. I wanted to get this up here right now for everybody. The top part's all my social stuff. The bottom part's all my all the DevSpace stuff. Reach out at any time if you got questions about the stuff. I love playing around with the stuff. If I don't know, you give me something new fun to play around with. So, you know, please feel free to reach out at any time. Hope you all enjoyed it and learned something. And yeah, questions, whatever you got. Your game for the YouTube videos? Yeah, I've really been wanting to get into more content creation lately, and it's just kind of, what do I start with? If you go to my YouTube channel right now, there's just 2 things of me doing the one chip challenge. Spoiler alert, it doesn't affect me too much. Oh, y'all are welcome. Like I said, any questions?
One thing I wanted to say back in the beginning where I mentioned that the add and the add overflow are both 1 byte. The reason was I was thinking that, if I were to explicitly throw an exception, like, if X equals null, throw new null reference exception, that would be several opcodes, several bytes. And I was just impressed that Microsoft built it like 1 opcode for the throw and even built that inside the add.
Yeah, I mean, that is a good point, is if you then did the check afterwards and whatever. But that's back to when I went to, they haven't revved the, they haven't put out a new version of the runtime in an extremely long period of time, and they've been doing compiler tricks, is that, I've talked to Mads at the C# team, and they're actually thinking about doing a new revision. Well, they are, because they get to do new revisions now with .NET 7 and 8 that are coming out. But one of the reasons, the good news of doing revisions and creating new runtimes is that they can start compressing all these codes and do those tricks, where it then becomes a 1 byte opcode and not compiled out hugely. Whereas when they're the compiler, but then the other side of it is, if I get my brain back to me, then people are installing and having to have multiple versions of the runtime on for compatibility. So they have to draw that line between how often do we want to make people literally install the new runtime, and how often do we just want to just do these compiler tricks. And it turns out people really don't like installing new hardware, and space is cheap these days. So they've just gone with the compiler tricks.
Yeah, what I was hoping for is that they, learn to inline lambdas.
Well, you can always do that. That's been there for a long time.
No, I mean, basically, when you do like a where, it'll actually create a new where clause with the, the part of the Lambda built right into the generated code.
Oh, I see. So there is a way to inline lambdas like I was doing with. I see what you're talking about. I want to explain this for other people and make sure I'm saying it correctly. There is a way to inline this stuff. You can inline that. Compiler services dot. Off the top of my head, it's like method impl dot aggressive inlining, and it's in compiler services. I would have to add the right, get the right using in there and whatnot. But you can look for aggressive inlining, and that tells the compiler, don't make this a method call, just drop this straight into code. So that already exists. But I see what you're talking about with link. But I think with link, I don't know if that would work because link is actually an overload on a functional, and the whole idea is to pass the function in.
Right.
So that's kind of, it almost defeats the purpose at that point.
Well, I mean, you would have like multiple copies of the where for every time you use it, but where itself is kind of small, so you're not adding that much space. And the actual comparison of the where in the Lambda is very fast. And so most of the time of that is calling the Lambda function.
Right. I mean, I suppose you could do it if you just created the function the Lambda was using as a method, even if you did it inline, and then you just told it to aggressively inline it, because that should pass the aggressive inline down to the actual interior function. But I would have to experiment on that. I'll try to experiment on that and post something somewhere.
That was funny. We both said, I'll try experimenting on that at the same time.
Yeah. So, but yeah. So somebody said something, name's cut off. Is it Andy and something? Anyways, slides are, the reason the slides aren't available is because they're mostly BS. If you want a copy of them, email me. I'm more than happy to email you a copy. I don't post these slides because there's not a whole lot in it. The code is not available because I actively wanted to encourage people to play around with the stuff themselves and get the tools. Having said that, just to open Windows Store real quick, because most of that code that you saw doesn't really do all that much. Should be ILSpy. Yeah, ILSpy. And this is what just drops into it's just a little WPF app. It does the exact same stuff. It's just not quite as user-friendly and not quite as pretty, but it integrates nicely into Visual Studio, and it supports F#. So this is the other tool I was talking about. I think they show in here somewhere. No. It may be an extension once you install it, but it will. The whole point of ILSpy is that when you're looking at your dependencies, you should be able to right-click one and say open an ILSpy, and it will just pull it up correctly. Any other questions?
And I think too, there's a switch in Visual Studio where it's the just my code switch. And so you can actually, if you take that off, if I'm saying this correctly, if you take that switch off, you can debug and step through the actual code that's in the .NET framework being executed. So
yes,
you kind of
absolutely can.
Yeah, see some of the magic behind there. The
Or
other
you
thing
can
I
just go to GitHub and read all the code.
well, that's where I was headed next is go to GitHub, go to the, because I've done this on projects where I've converted them from .NET Framework to .NET Core, is go find the source code and look at how things are done and how it's done differently. Things like I was looking at on a GUID, the get hash method on a GUID, there was actually calls to the like to the OS for doing integer calls.
Yeah.
to the OS. But you can't do that with Linux or, on .NET Framework on Linux. So that is completely done how they did that. So it was really neat to kind of see how that was different. So I highly encourage people.
Universal across the platform.
Right, exactly. And how they did it universally. And go explore, because it's fascinating stuff. Because a lot of times it's, well, I did this in .NET Core, now it's behaving entirely different in .NET Framework. Chances are you're relying on something you really shouldn't be relying on. That's what we found, is there was a reliance on the get hashcode method, the result of it. And when you went from one version to another heavy version, including .NET Framework, .NET Core, how it hashed was completely different. So the results were different. So if you're going to, so why use that at all? If you're going to do, say, .NET Framework 4.8, and that get hash code is going to be the same all the time. But
Yeah, and
if you go to, well, let me back that up. If you were like .NET 4.0 and then go to 4.8, it's probably different.
so who knows what the original default implementation of get hash code was? If you didn't specify a function, what did it do?
Just
No idea.
concatenates it all together, right?
What?
It just concatenates it all together, right?
No. That's what it does now.
CRC?
It returns the value of the pointer.
Ah, nice.
I knew it.
So literally it returned the value in the location in memory.
Okay, I'm glad they're not doing that now.
Yeah, I've seen
Yeah.
hashes that just return the first 4 characters and it's like,
Wow.
But considering for references, they only do reference checks for equality. By default, it made sense as a fast way to do it. Just return the 2 values of the pointers, and if they're pointing to the same thing, they're the same thing.
Okay. Yep. Which is a great discussion too, is understanding shallow copy and deep copy.
Right.
You're going to take a, like a collection, you're going to copy it. Which that's definitely on your to-do list, is go figure out what does that really mean. We don't have time tonight. All right, any other questions before we stop the recording?
I love your response, Gary. If it's stupid and it works, then it's not stupid. Yeah, because at the point in time when this happened, the heap was hidden very well. So you would have to do gymnastics to get to the heap. So it wasn't that bad, but it just didn't scale when things started moving across systems.